Hi, this is Raphael Mudge, the creator of Cobalt Strike. Welcome to Red Team Operations with Cobalt Strike, Part 3. This is Command and Control. In this lecture, we're going to talk about Malleable C2, which is a domain-specific language baked into Cobalt Strike that lets you change the indicators in the beacon payload. We will talk a bit about egress and network evasion, and we will talk about infrastructure OPSEC as well. I'll close the lecture with a discussion of Beacon's payload security model and how that works. Malleable C2 is a domain-specific language to give you control over the indicators in the beacon payload. Through Malleable C2, you can change what beacon's network traffic looks like. You can shape the in-memory content, characteristics, and behavior of the beacon payload. And you have fine-grained control over how beacon does process injection as well. Malleable C2 also has options to set advanced options in Cobalt Strike's post-exploitation DLLs as well. For this lecture, we're primarily going to focus on network traffic. This screenshot shows a snippet of a Malleable C2 profile that controls an HTTP GET transaction. And the other picture is a Wireshark screenshot that shows what this traffic looks like on the wire. Each team server has a single Malleable C2 profile associated with it, and that profile is specified when you start the team server. So do /team server, the address of the team server or the default redirector, the password, and the path to your profile file. Think of Malleable C2 as a mini programming language. And these malleable profiles have 4 components: options, blocks, extra indicators, and transforms. An option is the set keyword followed by a key. In this case, the key is user agent and a value. Here, we're setting the user agent value, which is a global value, and the user agent global value affects the HTTP user agent and all of the HTTP requests that the Cobalt Strike beacon payload makes. One other thing about options is that the option value is always wrapped in double quotes. So it makes sense that yes, the user agent block is global, or user agent option, excuse me. But options can exist within the context of a block. Here we have the HTTP GET block. And this is defining aspects of how Beacon does an HTTP GET to download tasks. And within this block, we happen to have an option URI. And the value of this option is /image/. In my documentation, you will often see me refer to an option that exists within a block like this. I might refer to it as http-get.uri, or I might do http get and an arrow pointing to URI. The main thing I want you to understand here is that options are a way of setting specific key value pairs, both globally and within the context of specific blocks in your profile. Blocks are a way of grouping indicators by specific behavior point. So here we have 3 blocks. We have HTTP GET, HTTP POST, and HTTP Stager. These are all very similar to each other, and they may have very similar indicators, but it would make sense you want to customize each of them separately. So that's why we have blocks, is to allow you to easily group the indicators related to these aspects of what Beacon does. So for example, the HTTP GET block is how Beacon downloads its tasks. Downloads tasks. The HTTP POST block controls how Beacon uploads output back to the Cobalt Strike team server. And the HTTP Stager block shapes the content of the staging process. We do have global blocks such as HTTP GET, which I explained a moment ago, but within each of our global blocks, there are sometimes nested blocks. And a nested block is a way of defining indicators for an aspect of what that block is controlling. So here we have the client block and the server block. And these are within the HTTP GET block. And the client block controls the HTTP request. It is the client-side aspect, or the client-side indicators of the HTTP request. The server block is the server-side indicators. It is the HTTP response. And it would make sense that we would have a client and server block when defining indicators for an HTTP GET transaction. Similarly, HTTP POST happens to have a client and server nested blocks as well. Extra indicators are a way of decorating aspects of a transaction. Here we have the header keyword, which is a way, in this context, of specifying an extra indicator. And this header keyword happens to accept two arguments. The first one is the key, or the header key, and the second one is the value. And we're specifying 4 different headers within the client block of our HTTP GET transaction. And so these headers will make sure that our HTTP GET request, the aspect of our Beacon behavior that is downloading tasks, it will make sure that the client side has these 4 headers. And that's the idea behind an extra indicator, is that you're, again, decorating the transaction. What about transforms? What are transforms? Transforms are a way of taking data that Beacon has to send. For example, metadata is a type of data that the HTTP GET client block has to send. And transforms are a way of dictating how Beacon should transform that data. And these statements are executed as a sequence, and they are used to derive a contract of how data is both stored in and recovered from a transaction. I mentioned that transforms, or data transforms, create a contract for how Beacon sends data and how it receives data. Let me explain how that works. Here we have the metadata block. The metadata block is a block, and within it are several data transforms. And these data transforms describe what we want Beacon to do with the data to send it back to Cobalt Strike. And we've got 3 steps. We've got NetBIOS encode, append dash.jpg, and URI append. We're going to walk through these. So our beacon wants to send metadata as part of an HTTP GET client request. So it's the client side of the beacon trying to download tasks. So we want to send this metadata. The first step we take is to NetBIOS encode that data. And NetBIOS encode is a way of taking a single byte and representing it with 2 characters in the English alphabet or the Roman alphabet. So you might have, and that's how that works. So you got GN is M, E is GF, etc., etc., etc. So our metadata becomes this. This is what our metadata becomes when it has been NetBIOS encoded. If we wanted to, we could NetBIOS encode twice and make this thing twice as big if we really, really wanted to. And there are other kinds of encoding options too, such as base64 or URL safe base64 and some other things there as well. The next step is step 2, because these are executed in order. And step 2 is to append dash.jpg to our NetBIOS encoded metadata. And so when we apply that step, we end up with this value. The final step is URI append, and that is called, in the data transform language, that is called a termination statement. And what it does is describes where to store the metadata in our HTTP transaction. And so different types of termination statements are available in different contexts. Here in a HTTP GET client block, we have the option of doing URI append to stick the resulting thing onto the end of the URL. We also have the option to stick the resulting thing into a header or a parameter. And if we're doing an HTTP post to send our data back, we have the option of using print as a terminating statement as well. So again, a lot of flexibility. And this is the point of Malleable C2, is I like to refer to it as user-defined storage-based covert communication. You are defining what you want to have happen to the data and telling the product where to store that transformed data. Now, what's really, really cool is this description allowed us to encode the data and store it somewhere. But what I'm going to show you in just a second is that we can follow this backwards to recover the data. And that's the beauty of Malleable C2 and how all of this works. So let's look at the receive side. We're going to use, again, the same metadata block, but instead of following the metadata block to send the data, we're going to instead work backwards and recover the original metadata. So when we're doing a recovery of data, we're actually going to follow these steps backwards. So let's go ahead and start. First, step 1 is to retrieve our encoded blob from where it's stored in the transaction. So in this case, that's in the URI. So we strip this thing off of the URI. And so we've got that. Next, we go on to step 2, which is to append dash.jpg. The inverse of appending 5 characters to a string is to remove 5 characters. And that's exactly what we're doing right here. We're just removing the last 5 characters, doing the inverse of that step. And what we end up with is this string right here. And likewise, for step 3, which is the NetBIOS encode step, when we're doing a recovery, the inverse is to decode. So we're just going to do a NetBIOS decode, and we end up with the metadata. And that's how a data transform works to recover data. Let's walk through some key Malleable C2 blocks. HTTP GET is the block that influences how Beacon downloads tasks. Now, the client side of this transaction is responsible for sending metadata. So every time Beacon connects to its team server to request tasks, it is sending metadata, which is an encrypted block that has, an encrypted blob that has information about the session. This encrypted blob needs to be transformed and stored somewhere in the transaction. Likewise, the server has a responsibility to send the encrypted tasks back to Beacon. And so you can shape that with the HTTP GET server output block. And so that's where you control what those encrypted tasks look like, or at least decorate them. The other block I want to speak to is HTTP post. HTTP post, again, controls how Beacon sends output back to its team server. The client side does double duty. It has to have an ID and an output block. The ID is your Beacon's identifier, it's a number, and the output block is the output Beacon wants to send back to Cobalt Strike. And this output can get quite big unless you enable chunking, which we'll talk about in a moment. But know that the HTTP post client block has these two items that it needs to transform and describe where they're stored in the transaction. The next key block, it's one that doesn't get much attention, is the HTTP stager block. And once again, this controls the staging protocol. So when a tiny stager reaches out to your team server to download the Beacon payload, this block controls some of those indicators. And the HTTP stager server output block is your chance to transform the encoded blob with your Beacon payload. These transforms are a little bit limited because stagers can't reverse base64 and NetBIOS encoding, but you can do things like prepend and append strings to that blob, and that can take you pretty far. Another important block getting its first mention in this lecture is HTTP config. And this block lets you set server headers and server header order for every single HTTP response your Cobalt Strike server makes. So you can think of this as almost a global server config more than anything. HTTPS certificate is the block where you set options to configure your SSL certificate. And there's a few other ones here, stage, PostX, and process inject. We'll go into those with more detail later. A code signer, I'm not going to mention in this course, unfortunately, but I recommend you take a look at it. This is a block where you can configure a code signing cert, because Cobalt Strike, when it exports an executable or DLL, does give you the option to sign those files if you have a code signing cert. Riddle me this, Batman. Which of these Wireshark screenshots is Beacon sending data back to Cobalt Strike, and which of them is Beacon downloading tasks from Cobalt Strike? It's a trick question. I don't actually know the answer, not anymore. But this is a good point to introduce HTTP GET only C2. This is an option with Malleable C2 to configure your profile so that Beacon sends data back to Cobalt Strike in small chunks rather than sending it back as a post request. The mechanism for get-only-C2 really has nothing to do with gets. In fact, I just call it chunked output internally. And here's how that works. Normally, the HTTP post client output block uses the print statement for its data termination statement. And that means post this data. So send it as the post output. But if you don't use print here, and instead use URI append, parameter, or header, Cobalt Strike will chunk the output instead of sending it as one big blob. And those chunks will be suitably small to fit into the URI, to fit into a parameter, or a header. In fact, they're the exact same size as the metadata that is sent in the HTTP GET client block. So that's output chunking, and you turn it on just by not using the print data termination statement. So if you want to do get-only-C2 and you're really interested in the get verb, you can set that. In the HTTP post block, set the verb key to get. And when Beacon sends data back to Cobalt Strike, it will do a get and not a post. Interestingly, if you really want to, you could, let's see if I have a purple here. I do. Or no, a brown. But you could do this. You could do HTTP get, and you could do set verb to post if you really want to. Let's do that. Post. So again, chunked output has nothing to do with the verb, but you have the flexibility to make that what you want. So if you want the HTTP post block to do gets and you want the HTTP get block to do posts, you can. No problem. The other thing too is the HTTP post block does have to send back the ID for the beacon in its client block. So if you want to, you could keep the verb post and use print here. And you could actually post that very small piece of data if you want. But if you're not wanting to post at all, then just continue to stick this value in a header, in the URI, or in a parameter. Another malleable C2 feature are profile variants. Right now, I've showed you HTTP GET, POST, and Stager, and just described them as ways to change the indicators for the HTTP and HTTPS beacon payloads. The problem is you have one profile per team server. What do you do if you want to stand up multiple listeners that each have different indicators? Well, this is the problem profile variants help solve. And here's how it works. When you specify a block like HTTP GET, you can optionally specify a variant name. And a variant is basically a variation of the current profile. So it is the current profile minus the blocks that you specify for that variant. And you can pack as many variants as you like into a single profile file. And you can make each variant change the profile as little or as much as you like. So if you want to have a variant X that redefines the GET, POST, Stager, and certificate blocks, you absolutely can. But if you want a simpler variant, maybe a GET-only variant, then you could just have that override the HTTP post block, and then the other blocks will use the default blocks in the profile. So that's profile variants. And of course, you can choose which profile variant you want when you create a new HTTP beacon listener. They will all show up under the profile field, and you can choose those right there. Whenever you make changes to your profile, you should always check the new profile with the C2Lint tool. C2Lint is distributed with the Linux package of Cobalt Strike, and it allows you to kind of unit test and preview what your profile looks like. I want to walk through editing a profile with you just to kind of make what we talked about in the slides more real. We're going to jump over to a Malleable C2 Profiles folder. This is a folder with example profiles pulled from my GitHub repository. And the profile I'm going to grab for now is etombot.profile. The reason I'm grabbing this profile is it's the one featured in the slides we just went through, so it'll make a little bit more sense. Here's our etombot profile. The global option sample name defines what this profile is in our reporting engine. We're changing the sleep time of the tool and setting a user agent that will propagate to our different HTTP transactions done by the beacon stager and payload itself. The HTTP GET block specifies how beacon downloads tasks, and we have the client side of that and the server response. We also have the URI that the request is being made to. Within the client block, we have decorative headers, and we have a metadata block, which indicates how the client sends metadata back to Cobalt Strike, back to our team server, when we do an HTTP GET transaction. And here's how we're transforming the metadata. We NetBIOS encode it, append dash.jpg, and we stick that whole thing at the end of the URI. So that's that. In the server block, we have several headers, and the server sends output, our encrypted tasks, and we base64 encode them and send them to the client. So that's what's going on there. Here we have the HTTP post block, same story over here, except we are configuring what Beacon does when it sends output back to Cobalt Strike. Let's come over to the Cobalt Strike folder, and I want to show you C2Lint, which comes with the Linux package for Cobalt Strike. And C2Lint is a really cool tool. It is a true linting utility. Yes, it will catch syntax errors, but more importantly, it generates several representative transactions and tries to simulate what would happen in a HTTP transaction and signal to you issues regarding data corruption, things that are not RFC compliant, and things that it believes would break WinINet or the overall contract of what the client and server expect. So it's definitely a very, very cool tool. One thing it does do is it generates a preview of the different blocks you specify. So here's our HTTP GET block, and there you can see our representative NetBIOS encoded and dash.jpg appended metadata. Here's our decorative headers and our user agent. So that is that. And here we have the server response. Looks good. And we have the same thing for our HTTP post block as well. The green lines represent things that were passed, like checks that were run. Everything was good. Yellow is a warning. Sometimes warnings are related to feature degradation, saying, hey, the way you configured this profile is not OPSEC safe, or the way you configured this profile breaks certain features. So warnings you should pay attention to. And it's up to you whether or not you really want to use the profile with that warning. Sometimes it's okay, sometimes not. I mean, that's up to you. C2Lint does report errors as well. Let me show you what that looks like. If we make a syntax error, let's just change that from header to heater and run C2Lint, you see that we will get a few different errors because it's trying to guess what's going on. And it's telling us that we have an unknown statement at line 51 within the HTTP post client block. Go figure, line 51 is right here. That's our heater keyword there instead of header. So that fixes that. What about behavior errors? Well, let's generate a few. Here we have the metadata block, and we're transforming our metadata, sticking it in the URI. Common sense says that there is a limit to how long that URI can be. So let's force that. Let's make this a really long block. We'll just NetBIOS encode our metadata many times. And hey, we'll base64 encode it, mask it, NetBIOS it one more time. You can chain things together like this. This is kind of the point of Malleable C2, is to really let you decide how to transform and decorate these aspects of your data. So that looks good. And let's make the accept block, excuse me, not accept block. Let's just add a couple extra headers. We'll accept A, B, C. The reason I'm putting these extra headers in there is I secretly know, although I'm telling you, so it's not secret, that there's a limited amount of space for these programs inside the Beacon payload. So I'm really kind of breaking this profile in different ways. So when we run C2Lint, we get warned that the URI line can get pretty big and that we need to fix that so that we don't actually break what is acceptable within the HTTP protocol. And that's what the red line is here. That is an error. You always want to fix errors or else bad things are going to happen. So here's our very long, very blown up HTTP GET URI. So that's that. And you can see it's also complaining that the client block is too big when we distill it down to what will get patched into Beacon, and that we need to reduce that size. So that's a little bit on errors and how those work. And I'm just restoring the profile to where it was. Running C2Lint again, and we're good, real good. Now let's go ahead and just change the profile up just to give you an idea of some things that we can do. So we have our HTTP GET block, and I want to move some things around. Let's take our pragma and cache control blocks or headers, put them down here. I'm okay with accept up here, but let's take refer and use that as where we store our metadata. So what we're going to do is get rid of that. We're going to come in here and we're going to URL safe base64 encode our metadata. We're going to prepend a Google refer to it. And we'll put something like that, and underscore S in there. And then we're just going to say, stick this in the referrer header. And let's get rid of that. And let's change our /image to foo.jpg. Why not? And I think this is okay. Let's come over here and run C2Lint. And if we scroll up, you can see we have our image foo.jpg, our accept header, our refer header with some base64 encoded stuff. Shh, that base64 encoded stuff's our encrypted metadata. And we have our pragma and cache control headers and our user agent. Cool, right? So that's a good change. Let's play around a little bit with the output, the server side. First things first, we're going to do image JPEG is a content type. And we're going to get rid of the base64 transform. Let's leave this not looking like anything's plain text. And let's try to prepend some valid data. Let's see if we can find something that looks like a JPEG. I might actually have one right here. Let's see. I do. Icon.jpg. Perfect. I'm just going to do a hex dump-c on icon.jpg. Grab the first few lines. And normally you could stick a really big file in there. Like you could take most of this JPEG or all of it if you've got a one-liner that will transform it how we need. But for this demo, I'm just going to grab the first line of this JPEG. And I'm going to use that as just a fake header to prepend to my output. And so this is just a way that you can help get by some types of network security monitoring, actually. Because something might look at the image JPEG content type and say, are there the right magic bytes indicating this is a JPEG? And if you have them, or even have a full JPEG right here, you might get a free pass. So that looks okay to me. Let's come over here and let's run C2int on our eTimbot profile. And there you can see our representative data prepended with at least a few bytes from a JPEG header. So that's an example of changing the server side to something more plausible. We're going to change up the post side just a touch, and then we're going to do a profile variant, and then we'll start testing all this out with Wireshark. All right, let's come over here to the server side, or excuse me, the HTTP post block. For some reason, I was saying server side, and I have no idea. All right, let's change this up a little bit. First thing, personal pet peeve. Your content type in an HTTP post should never be application octet stream. I don't think any browser does that ever. So let's make this something more legitimate, like the www form URL encoded content type. So let's go over to our Malleable C2 profiles directory. And I'm just grepping for that content type because I can't remember it. All right, let's grab that, copy it to the clipboard, come over here, paste it into our profile. A little bit better. Get rid of that refer, that's kind of whatever. All right, cool. I'm happier with this. So our client block has to send our ID for our beacon, and it's doing a NetBIOS encoding and appending .asp to it and sticking it onto the URI. I am okay with this, so we can leave that. Actually, let's do something a little fun. I want to demonstrate one other thing just because I haven't done it yet. Let's make this a parameter. So let's do this. Let's prepend. We'll say I for index equals. Actually, if we just do parameter I, that'll do everything we want. Excuse me. So if we do parameter I, this NetBIOS encoded thing will be stuck into the URI as I equals whatever, whatever. One of the reasons we specify everything component by component, header, 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 parameter, instead of just building up the string ourselves, is because within WinINet, we build out the transaction that way. And within the server, we parse the HTTP request we get and break it down into these kinds of components. We will break it down as a server into a parameter or into individual headers. And so being able to specify everything that way makes sure that when the transaction is built, it's built in a way that we can pull the same data out. For whatever that's worth, just explain why we're doing things the way we are. All right, let's come over here to the output block, which we're doing a print, which is a way of saying that when we post data, this is what the client is sending after it sends its URI and headers. So let's change this up to look a little bit more plausible to this. We're just going to do, let's do a prepend, and we'll say content equals something, and we'll append. We'll say number equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. We'll ampersand submit equals submit. I'm just trying to make something that looks like plausible URL encoded form data. All right, I'm kind of comfortable with this. We'll talk about this a little bit later, but on the server side, the output block is there, but there's nothing being transformed. So this base64 statement is redundant. So we could just prepend something if we want to give it something to base64 transform and send in response. That's okay. But either way, let's do a C2lint and let's see what our post block looks like. And there we go, whack history, whack. I equals this stuff, content type, everything looks good. And there you can see our content equals our base64 string. And we've got our number and submit. Some things I'm not happy about. I'm not happy about that double equal sign, and we forgot an ampersand. So I'm going to change that real quick because we're trying to look at this and look at it like a critical thinker, make it better. Let's do URL encoded base64, C2lint, and there we go. I think that looks a lot better. And that's the value of playing around with C2lint, is just trying to get this stuff a little bit better. All right, anything else we want to do here? Let's take a look at doing a profile variant. I mentioned that a variant is a way of specifying one or more blocks that are variations of everything else in this profile. You can think of it as a way of having multiple profiles in one file. So I'm going to copy our HTTP post block, and I'm going to do a get only variant. And that's how we specify a variant, HTTP post get only. And we're going to make this a variant that allows us to send data back by chunking our output. So first, let's set the verb to get. Let's get rid of this content type header because we don't need it. We're not posting data. The parameter I is okay. I'm comfortable with that. And what about the output? What should we do with it? Let's make this output. Actually, we can do something like this. We can stick it in a parameter called content. And let's make a few other decorative parameters because I haven't shown that either. Let's do a decorative parameter called number equals, actually I think we do it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Another decorative parameter, submit equals submit. And there we go. So this should be a variant profile that just chunks everything up and sends our data back as a parameter in our URL. Let's see how this works. First things first, when you run C2lint and you have variants, each variant is treated like its own profile. In effect, it is. It is a variation of the base profile. So we have our default profile up top, and our get only variant is specified afterwards, okay? And the get block is the same and inherited from the default, but take a look at our post block. We're doing a get on history. We still have our I equals, we have our content, we have number, and we have submit. So we've got our decorative stuff, we've got our headers, and we've got our fake output. Okay? So that's creating a variant as well. All right, very exciting, right? Let's try this out and take a look at some of this traffic in Wireshark. So first, I'm going to start a team server. Actually, we'll do it right here. So starting up a team server, password, eTimbot.profile. We'll start up our Cobalt Strike client, connect to localhost, and we're good. Let's go to Cobalt Strike listeners, press add, and we're going to make this the default profile first. Add a host. And here you can see when we click on profile, right? Default, get only, those are our variants. So if we had 10 variants in this profile, they would all be listed right here. But we're going to do the default. And I am comfortable with this. Press save. And let's go to attacks, web drive-by, scripted web delivery. Grab our listener, hit choose. We're going to do 64-bit payload, that's fine. And let's press launch. And we now have a PowerShell one-liner that will run our payload with the default variant. One other thing, we should start Wireshark. So let's go ahead and do that. All right, Wireshark is started. Make it start collecting data. I think this is okay with me. And let's run this on a Windows 10 target. Here I am, just starting our one-liner. Hit OK. Let's go back to Cobalt Strike. Here we are in Cobalt Strike. Couple things. You can see the download of our PowerShell script that was hosted. And now we're seeing gets on image foo.jpg, right? And if we follow the TCP stream, I hope you'll agree, this looks a lot like our Malleable C2 preview. So that's that. And there's our fake JFIF, our fake header. So that's looking pretty good to me. Let's close that. Let's come over here. We'll interact with the agent, just give it something to do. I'm just asking it to send output back so you can see the post when it checks in. There we go. Let's clear out of that. And there's our post. Oops, did I do it right? Follow TCP stream. And here's our post. You got post, history, our encoded ID. You've got some headers. Some of these added by WinINet because we didn't specify. And our posted content, right? And here's our base64 encoded random data. Again, I hope you'll agree, kind of cool. It looks a lot like what we saw in C2Lint. Let's hit close. Come back. And I'm okay with this so far. Now let's create a second listener. Come over here, press add. We're going to call this HTTP get only. Add a host. We'll do port 8080 and we'll use the get only variant. Let's go ahead and press save. And let's spawn this agent. So we'll just go right click, spawn, our get only. And we should get a new session. You can see it's the get only listener versus the default. That's important because get only is a more constrained channel because we're sending data back over HTTP gets. By the way, when doing that, expect it to be about as performant as DNS text records, at least for sending data back. It can take a while. And here we can see our traffic still. Everything should be looking for foo.jpg. So I'm not that worried about that. Let's see if I can filter to 8080. I think that's going to work. All right, let's send some data back over GETS. So let's interact. Let's do a PS. Come over here. And what you should see is a lot of GETS on /history. That is us sending data back over HTTP GETS. And that's the GET only C2. Let's take a look at one of these. And here you can see the GET. And you can see how that's the I variable, the content parameter, number, and submit, and some other values, and then our same server response. Let's jump into the exciting and woolly world of egress and network evasion. In our attack chain, I assume we have code execution, and we're going to talk about steps to ensure that you have positive command and control over your beacon payload. Here is the command and control problem set. In any type of modern enterprise, you should expect that there is a network firewall that is denying all outbound traffic. So you can't assume that you will be able to make a raw connection out of a network. The only egress that you should expect is egress that goes through a proxy device. When this happens, your attack traffic must conform to the expected protocol, and there are other checks that it must pass as well. You also have to evade any type of network security monitoring, which may look for known IOCs in your tool set or even suspicious IOCs in the request. And by IOC, I mean indicator of compromise. You also have to worry about the problem set of your infrastructure being identified as Cobalt Strike before use. And we'll talk about that when we talk about Team Server OPSEC. Okay, I want to share some details about how the HTTP beacon and its stagers, and I'm including the HTTPS beacon in there, deal with proxies. So the stagers and the HTTP beacon payload build on a library called WinINet, which is the Windows Internet API. This is the same library that Internet Explorer uses for communication as well. There's a number of benefits to using this library. The first is that we get proxy awareness for free. So if your beacon process is running in the context of a domain user and Internet Explorer can get out, you should be able to get out as well. Conversely, if you are not running in the context of a domain user, for example, if you are in a process context running as system, you have no proxy awareness and you are not getting out if there is a proxy required. So keep that in mind. The beacon payload, thanks to WinINet, will automatically authenticate to the proxy, and that works pretty well. One other thing is that the stagers, and only the stagers, will prompt the user if proxy authentication fails. And this is kind of one of those, I don't want to call it a hidden feature, but it's a feature that's there, particularly for assume breach exercises, to make sure your payload has a chance at getting out. If none of this works for you, or if you're in a context that is not a domain user context, you can use custom proxy settings. And in the last lecture, I showed how to set custom proxy settings in a HTTP beacon listener. I want to point out one small detail. When you use custom proxy settings, your beacon payload file or stage, that reflective DLL, is going to have that information embedded somewhere inside of it with its configuration. And this is a little bit of a risk, something you just want to be aware of and weigh. Because if that payload file is used in, say, a user-driven attack and ends up on VirusTotal, well then there's the risk that the username and password for that proxy are going to get exposed and found by somebody else. And that's probably a situation you don't want. So when you use custom proxy settings, be aware that you are embedding that kind of information into your payload, and that information can potentially get exposed by you doing that. The last thing I want to speak to is that you should be aware that your WinINet library may have a TLS limitation that is incompatible with your redirector. And this is one I saw a blog post about it. I had somebody recently reach out to me as a support request. But Windows 7 does not have the most up-to-date TLS stack. And the TLS options, some of the newer ones, are actually disabled by default. So if you're using something like Azure as a redirector and you have to deal with Microsoft saying we're only going to allow TLS connections that are this version and above, you might run into trouble because WinINet on Windows 7 might not be able to connect to that. And so that's something just to be aware of when you're setting up infrastructure and figuring out what's going to work for your target set. Let's talk about a few profile tips for egress and network evasion purposes. First, don't use a public Malleable C2 profile example in production. Or use it, but don't expect good results if evasion is your goal. I very much recommend that you take a public profile example and use it as a base and modify it. And if you modify it enough, you should be okay. The second tip here requires some explanation, but the gist is this. When Beacon checks in, that's the HTTP GET block, or when it sends data back to Cobalt Strike, that is the post block. The server output nested blocks determine how the output is transformed and presented to the requesting beacon. And by default, they do nothing. And where this is relevant to you is that the HTTP post block always returns no data. So if you don't do anything, every time Beacon sends data back to its controller, it's going to get an empty server response. Similarly, with the block to check in and download tasks, if there are no taskings, there's no output. And if that block is not doing anything to transform the content, you're going to get back a server response with no content as well. And that can be a problem. So here's our GET on some URI. And here's our response from the server. And we have all of our headers, but one of them is content length 0. This is a suspicious IOC or suspicious behavior in some contexts. So I do recommend you avoid this situation. And how do you do that? Well, you can do that with your Malleable C2 profile. Very simple. Just do in the server output block. Use prepend to prepend some data, whether there's data or not. And if you want to randomize that data, make it look different each time, use the mask command to actually XOR that data with a random key and prepend that key to the transform blob. And if you don't want something that looks like a binary mess, you can transform it with something like base64 to base64 encode it, and you can continue to decorate from there. But the point is make sure that your server output block is working with something, even when there is no data, no output to send in the case of HTTP post, or there's no output to send when there's an HTTP GET block being evaluated and there's no taskings. And so prepend is the way you can do that. The next one I want to speak to is the staging process for staging Beacon over HTTP. I very much recommend you take advantage of the HTTP stager block to change what staging looks like on the wire. And again, just let me explain what everything looks like and share how you can change that. So I mentioned in the first part of the last lecture that staging is a get on some URI that checksums to some value. And the response to staging is something like this. It's something like this. It's going to be HP 11200 OK. You're going to have a content type header. And the content type by default is going to be application octet stream. And you're going to have this, you're going to have your encoded payload blob. We'll say it's position 0. And that's it. That is the staging process and what it looks like. Now let me explain how you can customize this. You can use the HTTP stager block. And first, to change the URI, there are two options. There's set URI x86, and there's set URI x64. Even if you define these, Cobalt Strike will still respond to any URI that has that right checksum, and it will treat it as staging. But if you stay within the tool and use a stager, Cobalt Strike will use the URI set in your HTTP stager block. But these options are how you change the URI in the staging protocol. I do recommend that for the server side, I do recommend that you have a header and that you specify something better for content type, something better than application octet stream. Again, in some stacks, something application octet stream might get special attention. And this goes for all of your malleable C2 blocks, not just staging, but avoid application octet stream. The other thing I recommend is that I recommend you take advantage of the HTTP stager server output block to transform that output, which is this encoded beacon payload stage. Okay? And you may ask, why? Why should I care? Well, first, it is true that the staging process in Cobalt Strike does send a blob of data that is masked with a random key. Okay? So you don't have to worry that much about, say, a signature against this stuff. But at the beginning of that blob is a very small stub program that is responsible for decoding your payload in place. And so we call that a decoder. And while it is true that the decoder stub in Cobalt Strike staging encoder is randomized, certain bytes are actually predictable and are fixed. So 0, 1, 2, 3, 4, 5, 6. So if I were writing a signature against this, I would say if the byte at offset 0 is value D, and the byte at offset 2 is value C, and the byte at offset 5 is an exclamation point, and the byte at offset 6 is R, I might conclude this is the Cobalt Strike staging protocol. Okay? And it's very common to see rules that are written starting at some sort of observable boundary. These types of rules are a lot faster to process, much faster than doing a linear search looking for a substring of bytes. And the other thing too is the observable stuff being at some fixed boundary means the rule is more tightly scoped. So hopefully it's less false positive prone. Because if a rule is too noisy, it'll be taken out of production and it won't have any utility. So what you can do to push back on this or take advantage of this reality is you can use the prepend directive and prepend some sort of valid content footer or header, that maybe matches the content type you set. And if you prepend some data, okay, what you're doing is shifting that decoder stub down, and you break any rules that depend on looking for the decoder by observing fixed bytes from the beginning of the response. And this idea of prepending IOCs with junk data, I think is called binary padding. I think that's what MITRE ATT&CK calls it. It's a solid tactic. It's not going to work everywhere, but it is definitely a useful piece of evasion tradecraft. I do recommend that you use the HTTP config block to standardize server headers and server header order in all of Cobalt Strike's HTTP server responses. If anything, it'll save you the effort of populating the get, post, and stager blocks with the same headers. So you can think of it as a time-saving measure, but I recommend you take advantage of it. Another item is you should set a plausible user agent for your target network. So if you know the default browser configuration leaving the target network, take advantage of this global user agent option and set it to make sure that your beacon stagers and the beacon payload itself are always using a plausible user agent. Finally, if you're in a tough egress situation, consider using HTTP GET only C2, that chunking I talked about a moment ago. I would even consider it for your staging agent when you don't know what to expect out of the target network. HTTP GET only C2 is probably, in terms of the HTTP beacon, that is going to be your best chance to have two-way command and control over an agent with the least amount of friction. Let's talk about network security monitoring. Consider the use of an Apache server, an Nginx server, or a content delivery network as a redirector. This can help smooth out some Cobalt Strike specific indicators and even give you a better JA3 server fingerprint. Do invest in your infrastructure. Consider hosting redirectors on different providers. Remember that domains are better with age and categorization, a new domain is a potential indicator or something suspicious. Categorization is handy when going through a proxy that breaks up traffic into different categories and treats it differently depending on the category. Do not use IPv4 addresses for command and control. A host header with a dotted quad or an IPv4 address is again a suspicious indicator and something that might draw analyst attention. Also, do have a valid SSL certificate, and no matter what, do not use the default Cobalt Strike SSL certificate. And the other thing I want to mention is consider operating low and slow. There's a big difference in terms of how easy you are to observe when you have a beacon calling home multiple times a second versus once a minute, once every 5 minutes, or even once an hour. I recommend finding that threshold that's tolerable for you to meet your objectives, but allows you to stay under the radar of easily being seen. I want to talk briefly about using an Apache Nginx or CDN as a redirector for your Cobalt Strike traffic. So here I have a beacon making a GET request somewhere. To start, we'll have it make a GET request on our Cobalt Strike team server. And it's going to get as a response the typical HTTP 200 OK. And it might get back the few headers that are actually returned by Cobalt Strike, which is content type, date, and content length. So this might be a typical response from a Cobalt Strike team server with no configuration. Two potential tool-specific indicators are the order of these headers and which headers are present and which ones are missing. So that could be a potential tool to fingerprint this Cobalt Strike response. Now, if you use a valid server or a CDN in the middle, you're going to get back the same stuff, but it's possible you might have more headers, which will make things a little bit easier for you, along with the other things. And you're going to have the header order that is typical of that server. So that's another example of, again, smoothing out a tool-specific indicator by sending the request here, letting it go to our server, let it come back to the redirector and get decorated a little bit, and sent back to our beacon. And of course, you can change the header order in your beacon web server with the HTTP config block in your Malleable C2 profile. But there's another really cool piece of detection engineering I want to talk about because I think it's really cool. And it's called JA3. And I don't know if it's fair to say it was discovered or invented or how do you describe it, but either way, I do want to say I think kudos to the folks who came up with this. And JA3 is a way of looking at the handshake process of TLS traffic and generating a hash on the algorithms that both sides present to each other as potential key lengths and ciphers they can use to communicate. And it turns out that these presented ciphers and key lengths are a great way to fingerprint the applications on each side of a communication. And so what I'm doing is drawing my little envelope for these different parties. And I want to talk about JA3 because that is another reason to motivate using a proper server as a redirector. So if you look at the JA3 indicator of our HTTP GET, because the client side has a JA3 value, what you're going to get back with Cobalt Strike is the JA3 value of WinINet, which again is that library Beacon is using to communicate. And that happens to be the same library that Internet Explorer uses to communicate. So that's no big deal. But what about the JA3 value, or JA3, the JA3 server value, so JA3S of our team server? Well, that's going to be a slightly different story. What you're going to get is probably Java on Debian Linux or OpenGDK on Debian Linux. And that's going to be something that's going to stand out as slightly odd compared to other things. Whoops, and I'm just being pedantic and correct. This should be JA3S because it's the server side value. But if you do look at the JA3 value of your redirector, and that redirector happens to be Nginx, Apache, or a CDN, you're going to get back a value that matches that software. And so using a proper web server as a redirector is a way to smooth out this indicator, because having a communication that looks like it's between Internet Explorer and Apache looks less odd than something that looks like it's Internet Explorer and a Java application server on Debian Linux. If these kinds of indicators are a concern to you, then consider this my vote that it's a good idea to use an Apache server, an Nginx web server, or a CDN as a redirector. What about DNS command and control? The feedback I hear today is that DNS is a very binary thing with target environments. It's either something that a customer organization is blind to, or they have a decent handle on it. Here are the detection and prevention strategies for DNS. Split-split DNS is a prevention strategy. It's architecting a network so that workstations can look up internal resources, but they cannot make a query that would resolve something out on the internet. To get out to the internet, all of these lookups are instead delegated to the proxy server that host systems go through. So that's split-split DNS. If your compromised target can't look up the DNS record for something outside of your network, you can't communicate over DNS with Cobalt Strike's DNS beacon. A common detection method is to look at the volume of requests tied to a domain or subdomain, and organizations that do this will effectively have an idea of where there's potentially DNS tunneling taking place. The third type of detection strategy is looking for Cobalt Strike DNS command and control specific IOCs. The fourth is to look for bogon IP addresses. A bogon IP address is a DNS response that is observed that has an IP address that would not be valid, like 0000. The fifth detection strategy, looking again for something that is just abnormal, is to look at the length of request host names. A 200 character or more request host name is potentially a sign of DNS tunneling, especially when you tie that to a volume of requests. So here's how I recommend that you deal with this state of affairs. If you're in a network that does split-split DNS, don't use DNSC2. It's off the table. If you're in a network that is well instrumented to look for a volume of requests, I would use DNSC2 as a low and slow fallback option only. I would deploy an agent, maybe as a persistence agent, and configure it to phone home very, very, very rarely, like maybe once a day, once an hour, whatever. And just don't use it. And use it only if you need to, with the understanding it's probably going to get burned when you do use it. As for the content and tells in Cobalt Strike specifically, there are some malleable C2 options to change some of the DNS indicators. For example, DNS Stager Prepend and DNS Stager Subhost allow you to play around with the TXT record staging process. There's also an option today to set the time to live value in Cobalt Strike's DNS responses. As for Bogon IP addresses, there is an option in Malleable C2 called DNS idle. This allows you to change the idle response used by Cobalt Strike's DNS server. And this value is also used as a XOR mask for other signaling responses as well. So if you change DNS idle to something plausible, you will avoid Bogon IP addresses, at least for the TXT record aspect of the DNS beacon and the signaling piece. Don't use mode DNS though, because the entire 4-byte field, or the entire 4-byte response where an IP address would go, is used to send data back to you, and that will certainly generate Bogon responses at some point. In terms of lengthy host names and responses, well, you do have some play here as well. There is a DNS max text option in Malleable C2 to limit the size of a TXT record response when the DNS text record channel is in use. Similarly, the max DNS option will limit the hostname length when Beacon sends data back to you over DNS. Here are a few other details about DNSC2, just to kind of give you a full picture of what's going on. If you stage a payload over DNS with Cobalt Strike's DNS text stager, keep in mind it'll take over 1,000 TXT records to download the Beacon payload. The good news, though, is if the target host can resolve names, you can probably get out. And as for the DNS Beacon payload, there are options for DNS-A, Quad-A, and text records for C2. We talked about that in part 2 already. And I just want to remind you that each mode reduces the maximum hostname length. So DNS text will use 100% of the maximum hostname length, Quad A's will use 50%, and the A record channel will use about 25%. And the point of this downgrading of hostname length is to allow you to recover the agent if really long host names can't get out of the network, if that's something that's truncated automatically. I recommend that you take advantage of the SMB and TCP beacons for processes that need to run as system and target systems that cannot reach the internet. If you're going to use the TCP beacon for localhost only privilege escalation actions or to move to another context, take advantage of the option to create a TCP beacon that is always bound to localhost only. This may help you avoid some attention from the host-based firewall on that target. Pay attention to your communication paths. Compromised servers probably should not egress over HTTP or HTTPS. Remember that using the SMB beacon to go from a server to a workstation is weird. And if you scan to find targets, which does have its place sometimes, be aware that you're creating a lot of noise on the wire that could lead to detection. Some things to do. I recommend that you egress from plausible user processes on workstations. It's no longer enough to think about egress as egressing from the right system. Now you have to do it from the right process context as well. Do use the SMB beacon to go from workstations to servers. The SMB beacon is a fantastic pivoting option because the traffic is encapsulated in the SMB protocol. And going from a workstation to a DC over port 445 isn't that strange. Going from a workstation to a file server over port 445 isn't that strange. I do recommend you take advantage of built-in Windows tools and APIs to find targets. Querying Active Directory is definitely your friend, and we will talk about that later on when we talk about lateral movement. What is a plausible process for egress? Well, it depends on the type of C2 channel. But for example, for the HTTP beacon, I would think that anything that loads the WinINet DLL is a potential candidate for egressing over HTTP or HTTPS. Similarly, for the DNS beacon, anything that loads DNS API may be equally useful. Here, I'm using TaskList with the WAC-M option to look at processes on a Windows 10 system that load WinINet. I'd like to jump over to a discussion of infrastructure OPSEC. In the opening lecture for this course, I mentioned that threat intelligence is part of the red team problem set as it relates to positive command and control. The risk to your operation is this. You stand up a Cobalt Strike team server, it gets identified by an analyst, it gets analyzed, and insights gained from that analysis are packaged into a threat intelligence feed that your customer consumes and uses to stay ahead of your engagement. Now, it's perfectly plausible this is a desired outcome and something you wish to exercise as much as anything else. More power to you. Or maybe, for the kind of engagement you're doing, you don't really care if your information is in a third-party threat intelligence feed. Got it. But if that's a thing that is an item of concern to you, then we need to have a conversation about infrastructure OPSEC. In this slide, I'm showing a screenshot of a system called Censys. Censys is a company that scans the internet and collects meta information about all of these hosts and services they connect to. Censys is a system that I use and have used for surveying the internet looking for Cobalt Strike servers. When it comes to infrastructure OPSEC, there are 4 topics that I think are very important. The first is, which indicators does someone use with their own homegrown system or a system like Censys to find Cobalt Strike servers? The second is, how do they verify if that server is indeed Cobalt Strike? Third is, let's say you find a Cobalt Strike server, what information is available to an analyst who has sufficient knowledge of the tool? 4, the last question is, given all this information, how do you as a red team push back on this kind of analysis if you wish to do so? And these questions bring us here to questions 1 and 2. Let's start with how to find team servers on the internet. One very effective indicator is to look for servers that have the Cobalt Strike self-signed SSL certificate. Cobalt Strike ships with this self-signed certificate, and if you do not set an SSL certificate in your Malleable C2 profile, it will use this built-in one instead. And this is a good, very high signal indicator to use to find very default and unconfigured Cobalt Strike team servers. Another indicator is the Bogon IP 0000. In my own surveys, I've found this to be a very mixed indicator. Some servers that return this response are Cobalt Strike, as far as I can tell, and many others are not. A third one is to look for port 550, which is the default port of Cobalt Strike's team server. A fourth indicator, and this is a very effective one that can be searched with something like Census, is to look for any web server that has an empty index page, a 404 file not found error, and a text plain content type. This is an indicator of a Cobalt Strike server as well. Now, with all of these indicators, how does one verify if the system they found is indeed a Cobalt Strike server or not? Well, the way I do it is I connect to the server and ask it for a payload, and Cobalt Strike gives one to me. It has to, because this is Cobalt Strike's compatibility with the Metasploit Framework's staging protocol. Anyone can connect to the server and issue a request for a URI that checksums to some value, and Cobalt Strike will give back a payload. I spent so much time on staging in part 2 of this course because I wanted to make it clear that Cobalt Strike does support staging, and it's there to enable several features, but this particular feature and its benefits do create an OPSEC consideration. And this is it. So I'm foot stomping this pretty heavy. If you want to connect to your own team server and download a payload, you can with this wget recipe shown here. So, what kind of information lives inside of a Cobalt Strike Beacon payload if an analyst knows how to get it? Here's a screenshot from an internal system that Strategic Cyber uses as part of its payload surveys. And this is the information I pull out. So no surprise, but obviously the communication information has to live in the payload. If it's not there, the payload doesn't know where to communicate to. So the information that's there is the host, the port, the protocol, the user agent, and the URIs. I hope you can see that an automated system could very easily extract this information and build incredibly tightly scoped rules to identify this very specific traffic to these very specific hosts without false positives. So that's part of the appeal and power of doing this kind of proactive analysis. Other information about your beacon is in the payload as well. For example, the default spawn2 processes for temporary jobs are embedded in your beacon payload as well. Your sleep interval is there. Your DNS idle response is there. The name pipe is not there anymore in Cobalt Strike, I want to say 3.13 and later, but it was there in previous versions. My goal going through this information is to give you an idea of what insights live inside of a beacon payload and its configuration. I hope I've motivated the infrastructure OPSEC discussion and given you an idea of why infrastructure OPSEC is a consideration that should be up there with your egress strategy and your network security monitoring evasion strategy. Now, let me give you some advice on how to make your team server harder to find and how to make it much harder to pull information from your team server. First things first, do not use a default SSL certificate. You can set a valid SSL certificate in your Malleable C2 profile. I recommend that you do that. I also continue to recommend that you consider using an Apache Nginx server or a CDN as a redirector. Again, this can smooth out some Cobalt Strike specific indicators, and it can help with your JA3 server fingerprint. I also recommend that if you do use an Apache Nginx server or a CDN as a redirector, that you firewall your host to only allow HTTP or HTTPS connections from those redirectors. I recommend this step to keep your team server and its indicators, without the redirectors, out of systems like Census. For the Bogon IP response, just set the DNS idle value in your Malleable C2 profile. No big deal there. For port 550, I would recommend that you firewall port 550 and access it via an SSH tunnel. I know several of my customers do something like this. You can also edit the team server script on Linux to change the port from 550 to something else. What about the website content? Well, the easy way to deal with this indicator is host content on your redirectors or within Cobalt Strike. And I will show you how to push files to Cobalt Strike's web server in the next lecture. My last recommendation to make your team server less interesting is to make it so that a third party cannot connect to it and request a payload. And the way you do this is to disable payload staging, and you can do that in Malleable C2. That is the host stage option. When you set host stage to false, you do lose the benefits of staging. You lose the ability to easily receive a session from the Metasploit framework, and you lose the ability to use a user-driven attack that embeds a payload stager inside of it. In Cobalt Strike 4, this should not be that big of a deal, because in Cobalt Strike 4, most of your post-exploitation actions do not use stagers. And when they do, the stager is tightly coupled to the action and not itself dependent on it's not dependent on an internet accessible payload being hosted. If you want payload staging, I recommend you leave the option on your Cobalt Strike staging server. But for your long haul server, there's no good reason to have it. And for the server you're doing PostEx from, I recommend you turn payload staging off as well. In Cobalt Strike 4, I don't think you'll notice it very much once you have initial access. I want to cover a topic that is very important background information to have about any tool set that you're using. And that is, what are its security features? I want to cover what the security features are of the Beacon payload, specifically as it relates to its communication. So here they are. The Beacon payload, when it calls home to the Cobalt Strike team server, it does authenticate its team server. The Beacon tasks and output are encrypted, and Beacon does have replay protection for its tasks. These things are referring to the Beacon payload regardless of channel. So the SMB, DNS, TCP, HTTP, HTTPS Beacon are all the same. They all use the same scheme. One thing that is important to know, though, is that payload stagers do not have these security features. And remember, stagers are those tiny programs that connect to a server, download a payload, and pass execution to it. So when you use a stager, you have the risk that there could be a man-in-the-middle attack on your connection, and that exchange of downloading a payload is not encrypted. Let's walk through how these payload security features work at a very high level. When the team server is first run and creates a first listener, it generates a public and private key pair. Whenever the team server generates a Beacon payload stage, that stage has the team server's public key embedded inside of it. When Beacon is running on a target, the target generates a session key. So at this point, the target knows the session key and it knows the public key of its team server. It then encrypts metadata to send back to the Cobalt Strike team server, and it uses the public key, which only your team server can decrypt, to send this metadata. Included in the metadata is the session key for that particular Beacon session. Once the team server receives the metadata and decrypts it, it now knows the session key, which it can use to encrypt tasks and which the Beacon session, the Beacon payload, can use to decrypt. Likewise, when the Beacon payload has output to send to your Cobalt Strike team server, it uses the session key to encrypt that output, and the Beacon team server uses that session key to decrypt it. And that is the payload security scheme in the Beacon payload. In this lecture, we covered a lot of ground. I introduced you to Malleable C2, which is a domain-specific language to change what Beacon looks like on the wire and to modify other aspects of the payload. I also walked you through some ideas and tips for egress and network evasion. We also talked about how to make your team server less visible to folks looking for Cobalt Strike on the internet to package into their threat intelligence feeds. We concluded with a description of the payload security model and features in the Beacon payload. This concludes Command and Control, which is part 3 of Red Team Operations with Cobalt Strike.